There we go. Okay, now it's recording. Great. So, yeah, similar to what we kind of said last week, when it comes to aromatics, it's all about conjugation, and that's really what it all has to do with. And so, previously I had said that when you have, for example, a linear molecule, and it looks, let's say we'll give it 6 carbons, 3 double bonds. Just for the hell of it, we'll throw an sp3 carbon on there, and then we'll just point out like, oh, look, this is sp3, so we're really not worried about it. There are 6 carbon atoms involved in this whole like resonance structure, right? Because you can hop from here to here and here to here. And I guess you could hop here to here too and move on to either end. There are 6 carbons involved in this whole resonance structure. And so there's a formula, you could say, to write out all of the molecular orbitals. You could just follow this exact line of reasoning and it'll get you the answer every time, right? Okay, we have energy, right, going up. Okay, and then we draw 6 evenly spaced lines, as evenly as I can get them. We have 6 electrons total, right? So we fill in from the bottom in pairs. We draw a line halfway through, say that all of these are bonding, and these are anti-bonding, which I'm always too lazy to write, but I'm never too lazy to write bonding for some reason. Okay, and then, well, there's 0 nodes, there's 1 node, 2 nodes, and so on. And then if we wanted to draw our molecular orbitals, then let's say, 0 nodes, and I'm going to do it down here just for space. We have our whole molecule, right? We're not really worried about this last part. This is just like this extra part. We're not really worried about it. When there are 0 nodes, okay, that's pretty easy because, well, there are no nodes. So you just draw one big orbital like this, okay? And I'm using colors here, but you could write pluses and minuses too. So there we go. Okay, and when there's 1 node, you redraw the molecule, right? And then there's this extra carbon hanging off, but we're not really worried about it. But we'll draw it in for consistency. But there's a node down the middle. So we split this molecule symmetrically, and from there, we repeat. Except once we hit that node, we flip signs. Or in my case, colors, because I'm using colors. Okay, so there we go. Okay, let me get sloppy. Okay, cool. Right, and then you can go up and do 2, 3, and all those nodes, right? Okay, great. This is old news. This is like 3 weeks ago or something, or like ages ago, who knows. Cool. When you have a ring molecule, it's a little bit more complicated. And so why don't I draw, let me pick just a basic molecule. This is probably fine. Let's just pick benzene, I guess. When we have more carbons, then we have to like do a little bit more. We can't just draw evenly spaced energy levels, because sometimes when you draw a node, there are multiple ways to draw that same node in that molecule. So instead, what you do is you take this molecule and you redraw it, okay? And I'm gonna draw it in gray because it's like in the background. So you redraw this molecule. Here's your energy scale. And then you draw an energy level at each of these vertices. Okay. And the kind of important trick here is that, or one thing that you always have to remember, and maybe the most important thing, is that at this bottom, there's only one energy level. So the vertex is always at the bottom. One vertex, okay? You can't have two vertices. I know that, like, I think 2 weeks ago I had drawn this incorrectly. I was doing the structure for, like, I think this with a plus sign, and I accidentally drew two vertices, but that was wrong. It's corrected. The vertex is always at the bottom. Do you guys remember why?
Don't the second and third orbitals have the same, they have the same energy? I don't know if I'm really answering your question, but.
Yeah, so these two do have the same energy. Maybe let me ask this. So here, these two have the same energy because each of these has one node.
Yeah, the bottom one has to have 0 nodes, right? You can only get one, whatever arrangement where you have 0 nodes.
Exactly, yeah. There's only one way to draw this with 0 nodes. Okay, which is you just draw like the molecule itself. So let me draw this a little bit like funky. I'll draw it like really flat. So it's kind of like laying down. The only way that you can draw this is to draw, look, there's like a big node up top here, and underneath there's, or not node, sorry, there's this big cloud on the bottom. That's the only way you can draw it. You can flip red and blue, but that doesn't change like the shape of the whole orbital. In fact, that was like arbitrary as a choice. Like, we could have picked red on top and blue on bottom. So this is the only way to actually draw that. When there's one node, then you could draw it a couple of different ways. So you could have like, have it go through, I think it's through the bonds, and so you could draw it. Oh no, well, you could draw it either going through the bonds, or you could draw it going through the vertices. That's how you could have your nodes.
Actually,
and yeah, go ahead.
I just had a question on like when we're drawing, maybe we'll get to this in a little bit, but it seems like when we're drawing the like those horizontal, diagonal, or vertical lines, like there is an order to it. And I think it's like you first draw horizontal and then vertical, and then you do the diagonals. And I just didn't quite understand why.
Okay. Yeah, I know what you mean. Like you mean for these next ones, for example, the structure has to look like this, right?
Right.
And then the other way that you could draw it is to have, for example, a node here and one here.
Yeah.
Yeah, so do you mean between these two there's an order, or?
And even in the, I guess it would be pi 2 and pi 3, I think there was something in like the mastering homework that you had to kind of like match how they were divided. And I guess through process of elimination, I kind of like understood that I think the horizontal comes first before like dividing it vertically, but I just didn't really understand the logic or like the order of like dividing it in a certain way, because you're still dividing it in two, but there is like a way to divide it, if that makes sense.
Okay. Yeah, between like these two or between these two of the same energy level, they're the same energy level. So either order that you would write it in would be fine.
Okay, so there's not really then like an order between same energy levels.
No.
Okay.
No.
Maybe I was looking at that wrong.
Yeah, this position and this position here on the energy diagram are arbitrary. Really, they're like, we just use this to like, as like a visual aid. Really, the energy levels are just like next to each other, or really like, I mean, this direction doesn't mean anything, so it's like just kind of a visual representation. Yeah, I'm not sure. I guess I'd have to see like what the mastering thing was, what it was like asking or what it was about. It could have just also been another classic case of like writing the right answer and the computer like having a pre-programmed thing that just says like, oh no, you're wrong, even though you gave the totally fine thing.
Okay. So the thing to know is just like you can really divide it like vertically or horizontally as long as you're doing that before like the 2 crosses for the next energy level.
Yep.
Okay, that makes sense. Thank you.
Yeah. Okay. Yeah. And so really the only thing we did different here is that we just drew this polygon and there are, you can have energy levels at the same height. Otherwise, everything else is exactly the same. So we draw our line halfway through. This side is bonding. These are anti-bonding. Okay, this is 1 node, 0 nodes, 2 nodes, 3 nodes. All right, we fill in electrons from the bottom, going up. Cool, great. And this works in general. This is like a really pretty formulaic way. Once you have this like polygon drawn, and well, then from there you're good to go. We can draw like other rings. So let's say that we have this thing, a heptagon with 7 carbons, and let's give it a minus charge here, and then a whole bunch of these double bonds. Okay, well, we repeat the procedure. It's pretty formulaic at this point. So there's going to be 1 vertex at the bottom, and then from there, we fill in. Oh, well, this thing is even harder to draw upside down. Okay, great. And so there.
And is this guy anti-aromatic?
Yeah, exactly. Great. So we draw our line halfway through, right? And then we fill in from the bottom, and exactly like you said, this thing is anti-aromatic because at the end of the day, you have 2 electrons, and remember, we have this thing that's called Hund's rule. That's if you want to be fancy, but otherwise you can call it seats on the bus, which means that every electron or everybody who's on the bus will take their own seat before they go on and sit with somebody else, right? So these 2 electrons will fill in these like orbitals. No, yeah, these orbitals themselves first, and so they'll be like lone, and this will form a diradical. Okay, and so exactly like you said, this is anti-aromatic. Okay, in other words, this is like the whole origin of the rule, whose name, Huckel's rule, that's the name. So you get Huckel's rule, which tells us that if you can express the number of electrons as 4n plus 2, then it's aromatic. And then if it's 4n, then it's anti-aromatic. That's only if it's planar, though. Okay. And in general, if something has the choice of being not planar, then it will. And so the example that you must know, because it's like come up in every organic chemistry question in the history of ever, is that tetracyclooctene is this is non-aromatic because it's big enough to be planar. Like, and you have to know this one. It comes up every time. I mean, Dr. Tong might not ask about it because it's like a free point as long as you've ever seen this thing, but it's always one to know.
Wait, Adam, I don't know if I heard you correctly, but isn't it big enough to be non-planar?
Yeah, exactly. It's non-aromatic precisely because it's not planar.
Gotcha, because the p orbitals don't overlap because it kind of like turns into a little boat.
Yeah, exactly.
Right? Oh, okay.
Yep, it does this thing. And so the p orbitals don't overlap in the end of the day. Yeah, and then I guess just to like also mention, I've been doing everything so far with carbon atoms, but you can definitely throw in other atoms in there. And if they can be sp2 hybridized by giving up their electrons in resonance, then they will if it makes the molecule aromatic at the end of the day. So, for example, like, let's see. Let's see what a good example might be. Okay, well, maybe the classic is like furan, which is this molecule. Okay, and this oxygen has two lone pairs, and what it can very well decide to do is give one of those lone pairs into resonance. And so this molecule is actually aromatic because one of those lone pairs just resonates around the whole molecule. You get 6 electrons total. It's 4n plus 2.
And the reason we don't consider the second pair of electrons, is it because it's perpendicular to the plane or something?
Yeah. At that point, that pair of electrons actually would be exactly like you said. It's called orthogonal to the plane of the molecule. It'll stick out. That's actually a good point to mention, because something that's like really common as a question is to ask, for example, let's think about what this normally looks like. So a really common type of question, and it's one that you'll see a lot more later too, is that somebody can ask you, like, let's say you have this molecule and this molecule, and let's see. This one. No, that doesn't have a plus, actually. This is just normal pyrimidine. A common thing to ask is like, which is the most basic or least basic? I guess just rank basicity. The reason I say that this is like a really common question in 242 is because you also cover amines later, which are like cool because they're basic. And so this is like a common thing to ask. Okay. So I guess I'll just ask you guys then, because you have at this point everything you need to know to be able to rank these. Which of them is most basic?
Quick question. Is that last one basically a benzene with a nitrogen?
Yes.
Oh, okay. Got it.
I think the pyrimidine is going to be pretty basic.
Okay. What makes you say that?
Because the nitrogen's got a lone pair that can contribute to basicity because it's attached to a double bond.
Okay, so it has this lone pair, and this lone pair is orthogonal. Okay, good. So, and in comparison, or in contrast, this one is not orthogonal. This lone pair is caught up in resonance. Okay. And then an important question here is to ask, is this sp3 hybridized nitrogen more basic or less basic than an sp2 hybridized nitrogen? And this one you guys got to reach back for.
Could you repeat the question?
So is the nitrogen here or the nitrogen here more basic? Oh, what did I just do? Oh no. Let me hit Control Z a couple. Okay, cool. All right. I accidentally pressed something and that was bad.
I'm gonna go with the one on the left is more basic.
Okay, why?
Because what was the far right molecule called again?
Pyrimidine.
So pyrimidine pyrimidine is aromatic, so it's more stable, right? So wouldn't that stability possibly lead to the inability to be like as basic as this nitrogen that's just on a cycloalkane?
Okay. But this pair of electrons here is orthogonal. So it doesn't participate in the aromaticity.
Okay.
Yeah. So that's not quite it. Other thoughts? Do you guys remember how hybridization affects acidity or basicity? If you remember how it affects acidity, it's just the opposite for basicity. So that's good.
I think the orthogonal nitrogen orthogonal lone pair is going to be the most basic.
Okay.
And that's because I'm guessing that the sp3 hybridized nitrogen is going to be less basic.
Okay.
Isn't it like, is the trend with acidity like the more S character, right? That's more acidic.
Oh, okay. So yeah.
Wouldn't it be opposite?
Then I'm wrong. Then it's the opposite.
Yeah. Yeah. So technically, it's kind of like not really like the official way you're supposed to do it is just to take the opposite of acidity, but like, I mean, it works and it is correct. So it's the easiest way to do it. But yeah, it's the opposite. So sp3 nitrogens are going to be the most basic. So if we mark these, let's make this A and this B and this C. This means that A is most basic, and then B is second most basic.
I thought we were saying that C is the...
Sorry, yeah, C. I had them out of order. It is C, yeah. C is the second most basic, and then B is the least basic. Yeah. And this is like a common sort of thing that you'll get. Although it might come up more when it comes to amines, because like, well, that's when you're focused on amines, so it makes sense. Yeah. And then I guess other like things to worry about with aromaticity. If you have like a boron in the ring, for example, boron is perfectly happy being sp2 hybridized, but it has a lone pair. Well, no, it actually doesn't have a lone pair. It's just an empty orbital. So for example, like, let's say something like this. This boron has just a totally empty lone pair. Sorry, an empty orbital. I keep saying lone pair. And so what do we know about this molecule?
Is it aromatic?
Yeah, exactly.
So in Huckel's rule, N can equal 0.
Yes.
Oh,
Exactly.
okay, that's what confused me a little bit on the mastering. Okay.
So
Yeah.
even if the p orbitals aren't filled, that still qualifies as being overlapping. Like it's overlapping with the p orbitals of the alkene in the bottom.
Yes, it is. Yeah, because boron will happily be sp2 hybridized, and then if you like were to draw this molecule in a planar way, these are these two orbitals, and then the boron orbital, it'll line up with it just fine, because that'll make the whole thing aromatic. And so you'll get them connected. Yeah.
So this is a very non-basic molecule.
Yeah, the boron will. So it's a little bit weird to say that. It won't become anti-aromatic if the boron were to make a bond.
Mm-hmm.
So let's say the boron were to make a bond. Then, oh, well, I guess it has this lone pair over here too, right? This is just empty. Ooh, I drew this boron. There should be a hydrogen here. There we go. Okay. Or something else on that boron. Then it just has a lone pair. That's what it should be.
Okay.
Yeah.
So it's sp2 hybridized, so it's kind of just like middling.
What do you mean?
I guess that you know what, I think I'm thinking too much about the amines. Never mind.
Okay. No, I guess you have a point. It wouldn't really happily act as a base, because then it would have to break aromaticity.
Okay.
So you wouldn't quite want that. Yeah.
Gotcha.
Cool. Yeah, I think for the most part, that's pretty much all there is to say. I also had this one example, which those of you from last week might remember. If I draw, and this is like a super hard molecule to draw, this is an example that I really like. If I were to draw this molecule here, and then it has bonds here and here and here. You need to be really careful whenever you're looking at one of these problems, because things can be anti-aromatic, aromatic, or non-aromatic. And if there's an sp3 hybridized carbon, then it's usually going to be non-aromatic. But if you look at this molecule and you go through and you do it all, like you check each carbon for whether it has a double bond or not, this carbon here is sp3 hybridized. Okay. But that doesn't kill us here. We could still go all the way around the ring. Okay. We could look at all these carbons on the outside. Okay. And all of these here are going to be connected by double bonds. and it's all going to be conjugated. And then you could count the double bonds. There's 1, 2, 3, 4, 5. So there's 10 electrons. And so it's aromatic. Despite the fact that there's that sp3 hybridized carbon in the middle, it doesn't affect electrons going around. It doesn't affect the whole thing being planar.
But isn't that one of the criteria for aromaticity, though?
Is what?
Because it doesn't participate, right?
Oh, as long as it doesn't participate.
Yeah. Yeah. So this is kind of a weird like case or weird example, but it is aromatic. Yeah, it's analogous in some. It's weird because it connects like all parts of the ring, but it's kind of analogous to if you just have like, you know, a benzene or something, and it has this methyl group hanging off, but it doesn't care. This thing is still aromatic at the end of the day. Like this doesn't actually affect it in the same way that this methyl group that's just sitting in the middle doesn't affect the aromaticity of the whole rest of the big structure.
Got it.
Yeah.
Isn't there kind of like off of this when you have the fused rings? I feel like there may have been like a question too about when there's like a double bond almost like in the center of the fused ring, that doesn't count as part of the pi system, as part of the aromatic system. And is that just because actually I don't think I understood the reason why.
Okay. So you can have double bonds on a fused ring. Like, let's see, here's an example that I've seen before but don't remember the answer to. If you have, for example, something like this can be planar, and there's pi orbitals for every single carbon that's on there. So, well, you can get bonds, you can get conjugation everywhere. But the thing is, at the end of the day, that this molecule here has 8 electrons. Okay. Can this molecule be non-planar?
No.
No. I don't think it can. I don't think so. Let's say we were to move these all around. Yeah, I don't think it can, but maybe you could imagine some kind of weird stuff. So if you were to draw it this way, then you could, for example, draw these double bonds going like this, and because they're trans, they'll point down. No, it won't work. You can't do it. So this must be planar, and in which case it's, what is this molecule?
Anti-aromatic.
Yeah. Exactly.
So I'm also just curious if aromaticity like trumps, if part of it's aromatic, the whole thing's aromatic. Like what if we have a benzene attached to a cyclooctatetrene? Like would we consider that to be aromatic, even though
Yeah.
cyclooctatetrene, maybe?
Oh, yeah, because in this case, this part of the molecule would be aromatic and this part would be non, right? And so what would you call this molecule?
Non-aromatic, right? I mean, if they ask, like, I don't know, that's just the way I'm thinking about it. If you ask us if the entire molecule is aromatic and part of it isn't. No.
I guess so. Yeah, they probably wouldn't ask, like, classify this molecule as aromatic, anti-aromatic, or non-aromatic. Yeah, I guess you would say non-aromatic, but like it's kind of a weird question because part of it is aromatic. So like
I wanna side with aromatic. If we're saying methylbenzene's aromatic, I want to say that this one's aromatic though.
Yeah. I guess I don't know. It's hard to say. Like I don't know if you would call methylbenzene, if you would call it aromatic, or if you'd say like the whole thing, the molecule as a whole is non-aromatic.
Mhm.
I don't know. I guess it's hard to say.
Wouldn't include the methyl group, right?
What?
The pi system there wouldn't include the methyl group.
Yeah, it wouldn't.
Oh, this would. Okay. All right, I can get behind that.
Okay. It's I don't know. I think I wouldn't expect that you'd be asked a question that's ambiguous that way.
It's like philosophical. Yeah, that's
yeah,
fine.
right. Yeah. I wouldn't expect it.
Adam, I found I guess what I was trying to explain earlier about like when you have an internal double bond. So one of the homework questions was like 4 fused benzene rings. And I think like the feedback on that was like that there was like one internal alkene and that wasn't part of the aromatic system. So I think they were just considering like the outside double bonds, which when you did the counted up pi electrons that fit into Huckel's 4n+2 rule.
Did it look like this?
It was basically kind of like a cross almost, like one on top, then 2, and then one on the bottom.
Let's see, one on top.
Like 1, 2, 1, like hopscotch.
Yeah, and so something. I guess you mean like this?
They had it a little bit differently, but I'm wondering if this would be the same thing.
I'm not sure. Can you send like a picture?
Yeah, I'm wondering too if I could just like annotate, even though I don't have. It's basically like one benzene ring on top. Like if you're doing top down, like if you draw a benzene ring and then below that you want to connect like 2 of them, and then below those 2 you connect another one.
Is it directly like that? You can't do this. This is too many bonds.
I can try to send a picture later or something.
Yeah, sure. Send a picture. I'm not
Okay.
understanding. Yeah. Well, I guess since I already drew this molecule here, what do you guys think it is? And then I guess what about this one too?
Bottom one's anti-aromatic.
Top one's non-aromatic.
Yeah.
Yeah, so this one is non-aromatic, good, and this one is anti-aromatic. Yeah. Maybe. Let's think about it. I guess there's.
I'm wrong. It's aromatic. I counted 20, but it's 18.
Okay. Yeah. So this one should be aromatic too. In general, when you have like some number of fused benzenes, it's aromatic. Although I'm not sure about what Sophia was asking. So maybe there's weird cases of weird ways of drawing. Okay. Cool. Should we work on the problems then?
Sure.
I guess there's 5 of you guys and 1 of me. So would you want to just like stay in this one big room, or do you want to split into like one group of 2 and a group of 3?
I'm fine with staying together if everyone else is.
Yeah, that's fine.
Cool. So let's do that, I guess. Do you guys have the worksheet? Let me even put the problems on the shared screen so you can see it. There we go. Got it.
It's funny. One of these H2H is the exact same question, with the benzene attached to a cyclooctatetraene.
Oh, really?
Yeah.
Okay. Oh, but it says assume planar. All right.
Oh, okay.
Yeah. In that case, then we can do that.
Yeah. Okay.
Otherwise, it would just be
Gonna be kind of wacky.
Cool. So here's the first thing.
I just
then-
sent in the chat that like one example I had, but we can get to it at the end. I just figured I'd send it now.
Yeah, sure. I'll take a look at it while you guys think about these problems. Yeah. Go. Okay, cool.
This first one, are we thinking non-aromatic or anti-aromatic? Anti?
I said non.
Okay. Is it because there's no? Is it because that weird positive charge on that carbon?
Yeah, I don't think it's a conjugated system. But
Okay.
for D, for number 2, is that a positive charge above the point of the second cyclopentane?
Yeah.
Okay.
Yep. It is.
And for E, is that also a positive charge on the bottom left?
Yeah, it looks like it. I think it
Excellent.
is. Oh, look, we already did F. Nice. No, we didn't do F.
We did.
something.
Oh yeah, because that was a cyclobutadiene or butadiene.
Cyclopropene.
Oh, propene. Yeah. Okay.
Yeah, we did it with 3 carbons.
So what are we thinking for G?
G.
It's the one with that turd beetle on the phosphorus.
I said aromatic.
Okay, because the phosphorus or the not phos. Why can't it is phosphorus is P? Okay, it's because phosphorus can contribute an electron pair.
I was thinking the same thing as the p orbital, like empty orbital.
Oh, okay, gotcha. And for that kind of same logic, do you also say that F was aromatic?
Yeah, I did.
Nice. Did you say L was non-aromatic?
I said non-aromatic, but I didn't feel good about it.
I feel like it's because that cat like the positive charge there, because that
I think you can draw a resonance to like if you flip one of those double bonds to where the positive charge is, then you bring down. Can you bring down?
That's what I was thinking. It kind of allows itself to be sp2 so it can participate in the resonance.
Yeah.
And then you wind up.
Oh, so you're saying
if you flip around the bonds.
So it might be a sneaky aromatic.
Might be
I said aromatic because it's 10, right? So it's
Right.
as well as equals rule.
Yeah.
Good look, Thomas. That makes sense. Okay. And then what are we thinking about I? Are we thinking anti?
Isn't that a whole big cyclopentane or pentene doesn't it turn into non-aromatic?
I don't think it's aromatic.
Oh yeah, never
I think
mind.
the top nitrogen
Yeah.
could be, yeah.
Yeah, never mind. I totally neglected that cyclopentane just kind of hanging out on the left there. All right. And then for B, did you guys say non or anti? So I'm thinking anti, but
I said non, just because I remember like the cyclobutane wasn't aromatic in lecture. I don't remember why, but I said non.
Isn't the cyclobutane anti, I thought, or butane?
Yeah, I think so. Yeah.
Okay. I know according to Huckles it would be anti. I just don't. Yeah. Okay.
then for H, are we saying aromatic?
The anti-aromatic.
Did I count wrong? 2, 4, 6, 8, 10, 12. Yes, that is a multiple of 4. You are correct. And would J for like would J be non or would it be anti? Because could
I said aromatic
That's what I said as well.
because I think it reminded me of something from the homework, and I think that one was aromatic.
Because it's the same thing where kind of I think the positive charged carbon can be sp2 to participate in the resonance, and then it's 2 minus 2 is 0, which I get 0 counts for Huckel's rule.
but with the phenyl group though, if you do kind of like throw one of the double bonds like towards it, wouldn't that ruin aromaticity for the phenyl group?
I guess if you include the phenol, I guess, yeah, if you think about the phenol group, you get up to 8 on Huckel's rule, which wouldn't work. Because, right, 8 minus 6, because you have the 6 from the aromatic ring.
Yeah.
So it might be anti, you might be right.
I'm on team non, because I think that if you do try to contribute any of the pi bonds over to the positive charge there, it would destroy the aromaticity. So like you can't get a conjugated system out of it, but it's just a hunch. What do you think?
Move the one from the bottom of the triangle.
But even if you did that, then like either the like opposite.
Yeah, but they can all just, I think they can all conform to sp2, just like we talked, just like with L, they can all be sp2 to allow that bond, that double bond to resonate around.
Okay, I got what you're saying. Okay.
But yeah, I agree that it's probably anti because of the phenol group, because that gives you 6 more pi electrons.
So you're looking at 8 total. Okay. Perfect. I guess then we're done. I guess, or C, did you say anti?
See, I said aromatic.
Aren't there 8?
Are you able to count 2 from the nitrogen, or is that?
Yeah, I thought a double, like nitrogens that are double bound to, they do count towards aromaticity.
Yeah,
Yeah, but
I got anti-aromatic.
I got I think like the double bond counts in it, but the lone pair doesn't.
doesn't count. Okay, yeah.
I think so too.
Cool, then I guess we're good, Adam.
All right, there's my cue. Okay, sounds good. So, all right, well then let's look at it. This first one, if I heard, I think you guys said anti-aromatic. Is that the case?
Now that we've like had this full discussion about aromaticity, I agree that it's anti, not non, but.
Oh,
Yeah,
you guys said non-aromatic.
I would say anti.
I said non.
Okay. Okay, then Dean, why do you say it's anti-aromatic instead of non-aromatic?
Well, I originally said it was non-aromatic because I thought that positive charge disrupts the conjugated system. And like, because you have carbons going all crazy, but since you have that positive charge, you're able to kind of shift your double bonds kind of around it. So I feel like you are able to like maintain a conjugated system, but due to Huckel's rule, the 4M comes out to 4. So it'd be an anti-aromatic. So I wouldn't lump Thomas in with my my original thoughts. Now I get that's anti.
Okay. Yeah. So it turns this molecule is it is anti-aromatic. This sp2 hybridized carbon, well, this carbon here has to be planar. Whenever there's an ion on a carbon, it has to be sp2, and so that carbon has to be like this, and then yeah, you could draw the rest of the molecule in two.
Oh, okay. So it's unoccupied p orbitals are giving us a conjugated system.
Yeah. Yeah, exactly. And so there's this double bond and this double bond, and then there's plus charge here. So the electrons go all the way around. Oops, there we go. Yeah, so the electrons can go around, and there's only 5 carbons, so you can't force it to be non-planar. So in this case, it is anti-aromatic. Okay.
What was the condition you used to say that it couldn't be non-planar?
I think it has to be 8 carbons or larger. I'm pretty sure 7 carbon compounds can't bend enough to be
Okay.
non-planar. Yeah. Yeah, I believe that's the case. But once it's 8 carbons, it's for sure big enough that it can bend around. Yeah. Okay, and then, I mean, from there was also draw the molecular orbital diagram, right? And so, I mean, we already did this one kind of, so you draw the same shape, except at the bottom, there's a vertex. Cool, right? And then you fill in. Well, there we go. And there's a diradical. That's kind of unfortunate. Okay, and then down here, there's 0 nodes, right? So if we draw our molecule out, it'll be blue, 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 and blue, right? And then on the bottom, all of these will be red. Okay, great. Now we have to draw it for these other ones, right? And here we have 1 node. And so we draw these with 1 node each. Oh, simply. Okay, cool. And so one of the nodes, we can make it symmetric and it'll look just like that. And that's pretty easy. Okay. So we just flip around that node. The question is what the other node looks like. So do you guys know what the other way we could draw the node looks like?
Couldn't you just go through 2 bonds? Like if you cut through like right below that top 2 carbon line there. Oh yeah, like that too.
Yeah. So this is what it would look like this. Or we'd cut through 2 of the bonds. And then, okay, and then from there you can fill in. Okay, great. And then, well, up here, and then up here we can either, well, in general, we're going to cut through 2 bonds because we would prefer to do that. I think in general, it's preferable to cut through bonds rather than through atoms. And so, for example, that's why in one of these here, we cut through 2 bonds, and in the other one, we cut through 1 bond and 1 atom instead of cutting through 2 atoms. And so in general, we're going to cut, on this one, we're going to cut through 2 bonds because that's preferable. And then in one of them, we're going to cut through another 2 bonds. And in the other one, we're going to cut through 1 bond and 1 atom. Okay. And then, well, from there, you just kind of go through. Okay. That's on a node, so there can't be anything there. Means down here is down, and then here's up, and then here's down, right? And then you can fill in with the rest because they're just opposite. And so it looks like this. And there's nothing on this carbon here because it's on a node. Same with right here. Looks good.
Looks good.
Excellent. Awesome. Okay. Oh yeah, and then there's all these. I love these problems. So let's go through them, I guess. Here, there's these nitrogens, right? And each of these has a lone pair. But what do you know about the lone pairs on these nitrogens?
They're not part of the arithmetic for Huckles, so it's aromatic.
Yeah, so these are
Orthogonal?
both of these lone pairs are orthogonal, and so this guy is aromatic.
And that's
Excellent.
because, like, no matter the atom, it can only participate in one sort of, it can only contribute maximum of 2. So if you counted the double bond that it's part of and the lone pair, it would be contributing 4, basically.
Yeah, that's a good way of thinking about it. There are even some questions out there, and I even have one up kind of as a example, although I'm not sure what the answer is. I like to pull my problems from this one book, and there's a question which asks if this molecule is aromatic. It looks like this, and that's exactly the thing, is that of this triple bond, only one, like this one, does not participate.
Also, isn't this geometry impossible?
It's a little bit funky, yeah, because this should really be a straight bond.
But if you like extrapolated it and make it bigger, it's
yeah.
Okay.
Yeah, drawing it with the straight bond is just really too hard. If you like this is a buildable molecule, I guess. And we just draw it this way. Every once in a while you draw like triple bonded things bent anyway, just because it's easier to draw.
Got it. Thank you.
Well, why don't I ask you guys then? What do you think?
2, 4, 6, 8, 10, 12. Anti-aromatic.
Yes, I think it is. Or it would be non-planar if it can be. Let me see. I don't remember what the answer is. Oh, I don't know.
Can
If
it
I
be
have it.
non-planar?
So
I would
yeah,
guess no. I would guess it can.
let's. I guess anti-aromatic if planar. We'd write it. There's a fair way to do it. Let's see what this book says, because I pulled this problem on the spot, so I don't actually know what they say.
Technically, couldn't we build this with a molecular modeling kit? And if we can flatten it out, it'll be fine.
It's the other way around. If you can unflatten it in like a reasonable way without like manually bending the bonds, then it would be non-aromatic.
If you drew this molecule with an alkene instead of the alkyne, then it would be planar. So you add a triple bond in place of the double bond. Wouldn't that contribute even more to it being unable to bend around that point?
Yeah.
How many carbons we got?
Yeah, I think so.
Isn't there something too about like when you have the hydrogens trans, like, and there's like sterics inside, then that makes it non-aromatic?
Yeah, that is true. Yeah, in this case, well, we drew it this way, but it doesn't even really look like this, so it's hard to say. The problem in this book that I just pulled this from, I didn't read the problem thoroughly. It said, just say whether these molecules are aromatic or not. And they don't ask for non-aromatic or anti-aromatic. So we could just say, well, this is not aromatic, at least by the phrasing of this problem. Whether it's non or anti-aromatic is a much harder question. And well, I don't know.
It's not aromatic, though.
Yes. In the phrasing of this book, it does not display aromatic character. That's what they say. So, yeah, this is as an example. Whether it's non or anti, I couldn't really tell you. I'd also guess it's non-aromatic, but won't say that for certain. 'Cause I'm not sure. What about B?
Anti-aromatic?
Yeah, I think I remember you guys saying anti. Yeah, why is that? I guess it doesn't obey Huckel's rule, right? Is there any way for it to be non-planar?
No,
No.
it can't be non-planar.
No, I don't think so.
And we don't have to worry about like the methyl groups unless you had another group that was in a ring, right?
Yeah, you don't have to worry about them.
Okay. So like if they were 8 carbons long, we still wouldn't have to worry about them as long as they don't close another ring. Is that right? When determining
Yeah,
aromaticity?
that's right.
Okay.
Yeah. Yeah, there's actually an example, and I can't remember it now. I bet it's in the textbook. There's an example of some molecule that some people have made, or maybe it's on Wikipedia or something. I can't remember. And they put like tert-butyls on all of these or something like that. Or some... or some really big group. I can't remember exactly what it is. And like somehow we're able to make this compound. It's like really, really high in energy, but it's stable enough that it can exist temporarily. And so I know that like something of this sort has been made before. And I think it's stable enough for them to look at it, but I don't remember exactly what. I think it's on the Wikipedia. Maybe I'll check. Cool.
I just had a really quick question back to A. I just don't remember, what does orthogonal mean?
Yeah, that's important. So when you have like generally this really comes up with nitrogens. When you have this nitrogen, it's sp2 hybridized, and it has this lone pair, right? But its p orbital is already bound up here. Like, the better way to draw this is if I drew it like this, and this is like the much more typical way of drawing this molecule. So I'm just going to draw one double bond in. So its p orbital is already tied up here. That means that this lone pair is just sticking out to the side. It's not going to participate in resonance at all. It's in this remaining sp2 orbital that's just sticking out.
So is orthogonal synonymous to perpendicular?
Yes, it is.
Okay. Gotcha. Thank you.
Yeah. Okay. This is orthogonal. Right, yeah. All right, what about C?
Anti?
Yeah, I think it would be. Because look, this nitrogen, this lone pair is orthogonal here, and so it can't get involved. And then you have something that's planar on this side and something that's planar on the other side, and they're not gonna, there's no way for these two to bend. Another way you could think about it is that there's no way for this over here, which is like effectively a benzene ring, right? If you move this to here and this to here, you get a benzene ring over here. And there's no way for two substituents on a benzene ring to point up or down relative to each other. They're going to point exactly planar. And so that's one way you could think about it. You probably don't have to go through all that mental gymnastics to say that this is anti-aromatic. Okay, D.
No, wait. Is this anti?
D is 2, 4, 6, 8. I would say anti.
Yeah, I agree. It has 8 electrons, and they're all I mean, this has to be in a p orbital, and this positive charge or lack of electrons also has to be in a p orbital. Okay, so they're all sp2 hybridized all around. They're all next to each other, so they're conjugated, and there's 8 electrons. Okay, it's anti-aromatic. If you want to be fancy, and you can, it's cool to be fancy. So you can move this here, move this double bond up here, move this double bond down here, and push this one over here, and draw the resonance structure. And what you'll get is,
Totally conjugated.
yeah, exactly.
Also, this thing is super duper planar. You can't get it to not be
Yeah,
planar.
this thing, yeah, exactly. It is.
I was just I built the weird molecule you made just out of curiosity, and it's pretty planar.
Which one?
The
What, the
one with
one-
the alkyne on it.
Oh, really?
Yeah.
Dang. Okay. All right. Well, I guess in that case, it is planar. So it is actually anti-aromatic. Huh. So,
Mind if I see D again real quick? Just so I
yeah,
can-
yeah. Let me go back up.
Thanks.
Oh yeah. Sorry to interrupt.
Yeah.
All right, I'm all set. I'm in good shape.
Yeah. What about E?
Oh, non-aromatic.
Why is it non-aromatic?
Ooh.
I think it's aromatic. I think E is aromatic.
I think I changed
Dean
my
says non-aromatic. So what, like, part of aromaticity does it violate?
I forget whether I argued,
Oh.
whether we talked about this one,
Yeah,
but I would
no.
say aromatic as well.
Okay.
I think, isn't it going to fold? Isn't it going to be non-planar?
Well, if it would fold to be non-planar if it would have to be anti-aromatic otherwise. If it can be aromatic, then it'll do that. It'll be planar. Because
Okay.
aromaticity is low in energy.
So then it's going to be aromatic, I think.
Okay.
I guess I just get tweaked out by the positive charge. Confuses me. So it is aromatic. Okay.
Okay.
Got it.
Sophia, are you on board with aromatic too?
I just I'm looking at this again. Initially I put aromatic, but the carbon that's between those 2 double bonds that doesn't have the positive charge, isn't that sp3?
Yeah, it is.
Oh, okay.
Yeah. Yes. This carbon right here is sp3, hybridized.
So it's non-aromatic.
Good call.
Yep. P3. Yeah. Make this pen a little smaller. Cool. Yeah, so it's sp3, and that means this whole thing is non-aromatic. Good catch, Sophia. All right, cool. F,
Aromatic.
aromatic. Okay. Paul, you're on board?
Yep. Yeah, I'm on board. And I think
Sophia?
by the same logic, G is going to be the same thing.
Okay. Let's stick on F for a moment. Thomas, you're on board?
Okay.
Yes, because boron can contribute an electron there.
There's an important question. Does boron have an extra electron pair?
See, I actually put non-aromatic because isn't boron a weird one where it's like happy with 3, happy with 6?
My God.
Yeah.
Wait, but then why would the cyclopropene be aromatic, whereas this one's non-aromatic.
Whoops.
Because
Sorry, this one's
Yeah.
actually, it's not non-aromatic, it's actually anti-aromatic.
Okay.
I should have said.
Oh.
Oh, okay. There you go. That makes sense.
Because it behaves like the plus charge, but it doesn't contribute an electron pair.
Okay.
Wait,
Actually, yeah, that's a great way of thinking about it. Is that this boron, I mean, yeah, I guess it does behave as a plus charge. It's empty. It doesn't contribute electrons.
So for the one that we talked about before, the cyclopropene with the boron up top, that's only got 2 pi electrons, right? So
Yeah.
how do
Well,
we classify that?
Can't equals rule, n can equal 0.
Oh, that's what we were talking about? Okay.
Yeah. Yeah. It can be. Equivalently, another example that comes up every once in a while is exactly like this, just a positive charge instead. Either one of those is aromatic.
What about like, can we do an example where we have that same cyclopropene and then with a negative charge and a radical, just so like I can see the difference?
Yeah. So if we had a negative charge here, then in that case, these would all be,
Anti.
yeah. So this one would be, it would be 4 electrons, so it's anti. All these carbons have their pi electrons. They're all sp2 hybridized. Okay, all good, right? And then it's bad because it's against Huckel's rule. If we have a radical, oh, well.
It'd have to be non, right? Because it doesn't follow Huckel's rule.
Yeah, I guess so. Yeah, I don't know. Have you guys seen any examples where you're classifying aromaticity with radicals?
I don't think so. We've definitely had to draw molecular orbitals for them, though.
Yeah. You could totally draw one. You could draw one just the same as the other systems. I mean, maybe it's worth actually drawing it out too. In this case, okay, we have our point at the bottom, right? And then we draw our shape. And here's our orbitals. There's 1, there's 2, and there's 3. We fill in the bottom one. That's no problem. Okay, we draw our line. So the energy goes. And then we put the electron in one of these 2 orbitals. It doesn't matter which one because, well, they're both the same energy. This would certainly be unstable because it has, well, it is a radical and they're generally unstable. On top of that, it has an electron in the anti-bonding orbital. That's kind of ugly and nasty. We don't really want that either. So I don't know if we would classify this as one of the 3 non-bonding, non-aromatic, anti-aromatic, or aromatic. I guess it would be non-aromatic, but like, yeah, I guess so. But we don't normally classify radicals in that way. Maybe an exception to that might be, for example, and I've never seen anything given like this, but I guess in theory, there's no reason they can't. If we had a compound that looked like this, and 2 radicals,
Ooh.
it's kind of spicy.
That's crazy.
Well, what do you guys think then?
I'm going aromatic.
Okay.
Yeah, I'd say aromatic. I'd say aromatic because you have 6 and it's all beneath the anti-bonding line.
Isn't the hybridization of the radical sp3?
No, it's sp2.
It's sp2.
Yeah. Watch this. What if I do this? You guys are going to like it. All right, let me take this electron and move it here. Take one electron from there. Move it into that bond. Do this. And do this.
Oh, now you have benzene.
Yep.
Wow.
Yeah.
Neat.
So I just redrew benzene that way. Yeah, I picked benzene because I came up with this on the spot, and I haven't seen any other examples of this ever. But I guess there's no reason why you can't do a diradical that's anti-aromatic either. This would be a really weird question to get, but I suppose there's no reason why you can't. Yeah. Cool. How about G? What did you guys think?
I think we got aromatic.
Yeah. Okay. Everybody on board with aromatic?
Yep.
Yeah, it makes sense to me.
Okay.
As long as we draw in that mode there.
Yeah. Cool. All right. So you guys all got that. H, okay, if it's planar, although we said earlier that it probably wouldn't be, what do we get?
Called anti.
I think anti 3 times 4.
Yep.
Yeah. Yep. It's anti-aromatic. Yeah, I think you guys even said that one earlier. So sweet. I,
Non-aromatic.
non-aromatic. Are you saying because of this whole thing?
Yes.
Okay. Okay, let's just regard this part of the molecule then.
I still say anti because of 4 electrons. 4 pi electrons.
Okay.
I said
Which
non because of the other ring.
Yeah,
Okay,
I said
well, what-
non. If we just, yeah, I said non, but if we just look at that one, then I think it would be non-aromatic, the right side.
I think right side is anti, full thing is non.
Yeah, I'm on board with that one. With that.
Okay. Let's see. So you guys are saying that the right side is anti-aromatic?
Mhm.
Yes.
Yeah.
Well, half
Okay.
of it.
What about this?
Yeah,
Does participate
Ah,
because it's
okay.
orthogonal.
because the nitrogen can have it. Yeah, have that lone pair.
But then where does this hydrogen go? If this lone pair is orthogonal, then where's the nitrogen go?
The
Or
hydrogen.
the hydrogen. Yeah.
Yeah, what I've heard is that if you have a lone pair, it can participate because it doesn't already have one like a lone pair
Oh,
participate.
okay, and then
Right?
it's aromatic.
Yeah.
Yeah. Yeah. So this is aromatic. Precisely because it looks like, let's draw this in a kind of planar way.
Would you say we should just, like, the first thing to do when approaching these problems is drawing the lone pairs? Because for me, at least, I keep on forgetting lone pairs, and that's killing me.
Yep. I think you should. And also, like, more than that, you should consider whether they're orthogonal or whether they're available for resonance. These two nitrogens have orthogonal lone pairs. The reason is because they already have a double bond. This nitrogen doesn't have a double bond, so its lone pair is free. It can move around. And so then you get 2, 4, and 6. Okay. In general, you could take it as a general rule that whenever you have a double bond on that nitrogen already, then you have an orthogonal pair of electrons. If you don't already have a double bond on that nitrogen, then that pair of electrons can be active in resonance.
So does that make then the whole thing aromatic?
Yeah. Yeah. We'd probably, I mean, yeah, maybe this is like you might want to ask what Dr. Tong or the TA would want you to say, because of course they're the ones grading you. I'm not, but I would call this whole molecule aromatic. I would just say the whole thing is aromatic because like it's probably very clear that they're asking you just about this right-hand side. Although that might be something you guys want to clarify with him, just to be sure about what like the expectation is.
Mm-hmm.
Yeah. Let's see. Yeah. I just had an example. Let me see. Oh, I guess this would be an example. Let's say let's ask, okay. Okay, which of these is more basic? Again, because we're doing nitrogens again. So I guess the question would be like, compare the basicity of, let's say, this molecule and this molecule. There we go.
The right one is more basic.
Okay.
That's
What
what I
makes you
would
say
say.
that?
Because the left one is conjugated. The right one
It's conjugated to.
is cool, but it's also, isn't that really unstable?
Okay. Well, why?
Because it's a cyclopropane.
Oh,
Well, isn't
angle.
the right one right now has 4, so it's anti-aromatic, right? So it wants to give up that extra lone pair to get to aromatic.
Yeah. Yes,
Yeah.
exactly.
So what's the Lewis acid and base definitions? I don't even remember. If it's donator, then it wants to give them up, so it'd be more basic.
Yeah. So this is more basic. Because in its current state, it's anti-aromatic. But if you give it a hydrogen, then it's gonna be forced into sp3. And then it can't give up its it can't participate with its electrons in resonance. Yeah. The reason that by the way, the reason that over here I drew these two substituents is so that the nitrogen would have a double bond connecting to it from either side in the same way that this nitrogen has a double bond connecting to it from either side. It's a little bit weird, and maybe this isn't like the greatest comparison, but
Because the one on the left, if it gives up its electrons, it doesn't do, like, it can't conjugate everything anymore, right? So that's the issue.
oh, I guess even that too. Yeah,
Wait,
I wasn't even really considering that.
what was the first thing then? What was, Adam, the first thing that you were considering?
It's the fact that this molecule is anti-aromatic in its current state.
Oh, okay. Yeah. All right.
Yeah. Yep. That is totally why. Cool. Jay?
J is.
Oh, yeah,
Aromatic, right?
we were arguing about this one. I would say anti as well, I think.
Okay.
Oh wait, 8 plus 2.
Wasn't it 6 plus 2?
6 plus
6
2.
up
Oh,
here and
yeah,
two
yeah, all right.
down.
Yeah, you're good. Your math is better.
Okay.
Aromatic.
Now Adam's going to tell us we're all wrong. I don't think he's told us what it is yet.
Yeah. Yeah, I'm gonna tell you guys you're wrong. Yeah, it is aromatic.
Oh, but it's not
we
plain.
would say that. Yeah, it's not gonna be planar. So I guess it's weird because like the definition of what they tell you is aromatic is so like, I don't know, it's like pretty narrow, and this molecule is perfectly fine. It is stable. It is like happy as it is. It is lower energy than like both this part and this part are lower energy than you would typically expect them to be. And in the case of this molecule, there's certainly no reason that you can't draw it like this, right? Where the benzene ring is planar, like flat like this in the plane.
But I don't get how this isn't anti-aromatic, because like let's say you shift the double bond up and then you throw the positive charge on one of those bottom ones depending on where you shifted the double bond up, and then it's still totally conjugated, but you have 8 pi electrons.
So the reason that I drew it like this is because this way it's not conjugated, because you have the ring that's flat like this, and then the benzene is flat this way.
Oh, okay.
And you can't.
So do they just
conjugate the
not?
two like that.
So when we're saying it's aromatic, we're saying just the triangle is aromatic. Not to say triangle, but you know what I mean.
Yeah, I guess so.
I mean, obviously the benzene ring is aromatic too, but they're like separately aromatic.
Yeah. I wonder, maybe I'll go back to the definition of what they say in the book is aromatic. It says they meet the following criteria. The structure must be cyclic, containing some number of conjugated pi bonds. Okay, well, we're already screwed because this structure isn't cyclic to begin with, because it has this bond right here.
Oh.
Each atom in the ring has to have an unhybridized p orbital. Okay, well, that's everything has an unhybridized p orbital. They have to overlap to form a continuous ring of parallel orbitals. Well, these don't overlap. Okay. And delocalization has to lower the electron energy. That it does, but like it doesn't meet the other criteria, which is really weird because this is like a good structure. It lowers the energy. It's totally stable. Yeah.
So it's really because it's just not fully cyclic.
Yeah. What I'm saying is following the definition that the book gives, like you would just say that this is non-aromatic, because if you were to draw both parts in the same plane, then it would have to be anti-aromatic. Actually, really following the definition in the book, it's always non-aromatic because it's not cyclic. Right? I mean, this thing here just ruins you from the start. But that's ridiculous because this molecule is perfectly happy drawn this way. Both parts of it are aromatic, and like, you know, it's lower in energy, which is really what we care about and what matters. So I had this molecule being as aromatic because it's good and stable and happy exactly in the way that I drew it. Yeah, but if you're like really following, I guess, this definition in the book, which I don't know, it's like, I don't know if it's great, then it would probably just be non-aromatic to begin with.
So the book said aromatic? I'm confused.
So like going by the book, this would be non-aromatic.
Right.
I would say aromatic. I bet I wouldn't be surprised if Dr. Tong said aromatic too. Because like, I mean, I guess maybe in one way you can look at it by parts and say, okay, each part of it is aromatic, so it's all good. Yeah. I would go with aromatic. It's another sort of thing, as with one of these other molecules, and I can't remember, maybe someone wrote it down. Maybe to ask Dr. Tong or the TA about it, just because of what their expectation will be. I would say this is aromatic, and I think probably most people would agree. Despite the fact that the textbook definition is really narrow and says not. Yeah, it is worth looking into.
I guess
Okay.
that's why I'm kind of confused still on like because like if we're considering like these requirements of like the entire thing, like why wouldn't that left cyclopentene, like it doesn't, it's not planar, right? Given the sp3 hybridization. So that's
Yeah.
why I would say like that then throws the whole thing off, meaning it would be non-aromatic. But I understand why the right part of that molecule is aromatic.
Yeah. Yeah, I don't know. Hopefully, I mean, I certainly hope Dr. Tong will give like ambiguous questions like these are a bit. Yeah, I know, right? This part of the molecule, if you were to say this whole molecule is aromatic or not, like, no, this one isn't. Although the right part is.
I would write an answer saying this portion of the molecule is aromatic, but when considered as a whole, it's not aromatic, non-aromatic. Just cover my base. I don't know.
Yeah.
Yeah.
I think maybe I'll maybe ask Dr. Tong, because I feel like the first thing that he was stressing is like it needs to follow these requirements, and then you can look at like the other stuff. So if it doesn't even cover the bases with like those criteria, then it's automatically non-aromatic.
Yeah.
But yeah.
Yeah. I mean, in that case, yeah, ask him. He might say both of these molecules are non-aromatic. In which case, like, okay, you're done. This one it doesn't have p orbitals all the way around. This one isn't cyclic, so neither of them are aromatic. I mean, if that's what he says, then you should absolutely follow that, because he might be like really sticking by the rules, in which case, like, that's good, and you should follow that. Like,
if you're sticking by the rules, then it's non-aromatic. We don't even consider it.
Yeah.
Okay.
Yep. Okay. It's okay.
Aromatic.
Yeah, 10.
Yep.
Okay. Sophia, you're on board?
I said non-aromatic because
Oh,
I
wow.
was thinking about the H's contributing the steric hindrance. So I thought that automatically makes it non-aromatic.
Yeah, it does. This molecule, that is true. I know you mentioned it earlier, that's why I picked you up. Yeah, these hydrogens in this molecule are going to bump into each other, and you can't have them in the same space at once. And so it's going to tilt, like this part of the molecule is going to tilt up and this part of the molecule is going to tilt down. And so this whole thing is non-planar, meaning that it has to be non-aromatic. This is this one is kind of just another like remember this one example kind of question. Same with tetracyclooctene, the stop sign. That one too, like you should remember that that's non-aromatic. This one you should also remember that. All right, L, last one.
Aromatic.
Yeah. Awesome. I'm with you guys. Okay, cool. This is a plus right here. And you could play the same game that we did up here for D. You can move this over here, move this over here, move this one down. And that's it, actually. You don't even have to move these other ones. So you could draw this resonance structure and 7 carbons. Oh, that's right. And then there you go. You get this and fill in the rest. I like it. It's cool. Okay. Oh, someone's taking a screenshot. Why moved? Okay.
Oh yeah, I was just taking a screenshot. I just made the molecules for I and J, and I might send it to Dr. Tong just to see if what he has to say about it.
Yeah. That's fair. Let's see. All right. Well, the next one is here. So we have to tell, okay, are these, well, what about these molecules? Are they aromatic, non-aromatic, or anti-aromatic? Okay, well, we've done benzene and the stop sign for ages, right? We're not, I don't think these will come as any surprises. So, right, this is it's aromatic. Well, I have to catch myself. This is non-aromatic. What about this up here? 18 annuline.
The same steric strain thing.
I think this one's aromatic.
Aromatic too.
Oh, because it's too big to suffer from steric strain.
Yes, it is.
Okay.
Yeah.
Okay.
Yeah. How exactly would you know that? Because it's kind of vague. You could imagine if, I'm going to do something fancy here. If instead of these hydrogens, what if you just filled in with the benzene rings? Right.
That would be multiplying the amount of double bonds by what? 3?
Oh, well, don't worry about the double bond. I'm just saying, just to see that the hydrogens aren't big enough, right? Like, if you were to do this, like this would fit. This would be fine, the way it's drawn, at least. And then in here there would be other stuff, but we're not worried about it. We're just saying, filling in with these carbons would be just bigger than the hydrogens. But like I could draw this, like I just drew it and it works. So that's one way you could think about it, but that's like kind of unofficial. Yeah, so these are all hydrogens, okay. And then there's 18 electrons. You can go around the ring and count. And so this is aromatic. Oops. There you go. And then next up, as a follow-up to that one, is a question about heme, which transports blood or transports oxygen in blood. And it's asking about porphyrin, which is kind of the structure underlying it. Porphyrin actually underlies also chlorophylls and a bunch of other plant dyes. And so this is kind of like a general important class of molecules for living things. Well, the question is it aromatic or not?
Yes.
Yeah. Did you count the electrons?
Yes, there are 11 double bonds, so 22 pi electrons, and following Huckel's rule, it's aromatic, and there wouldn't be steric hindrance, right?
All right, I believe you. It's probably 22 electrons. It is aromatic for sure because, I mean, well, it's in all living thing or in so many living things already. So, okay, that's probably one reason. But then, yeah, you go through and you count all the electrons, and yeah, it works out. It is aromatic. I think by whatever classification you're using, this one is okay. It is definitely aromatic because you have rings, right? Like you have, here's a big ring, and then there's rings attached to it, right? So it's all cyclic, and it's all pi conjugated. So it is aromatic. It's all good. Yeah. Did you count these nitrogen electrons? Just checking.
Oh, no, I did not. So
I got 26 when I did that, so it's still aromatic.
yeah.
Yeah.
Always forget about that.
So we're lucky, right? We're in the clear because we don't need to, but they do participate.
Mm-hmm.
They can move around pretty freely. So it's 26. All right, cool. Last problem.
I've got to hit the road, Adam, but thank you so much.
Cool. All right, see you.
Yeah, I'm probably going to head out as well. Thank you. Have a good one.
Okay. Yeah. Here, follow Sophia then. Or you can go too if you're got somewhere to be. But
I'll stick around for number 4 for a little bit.
Yeah. Yeah, this is the last one, at least of the aromatic questions. There's an extra question on the worksheet, but it has to do with reactions on aromatic rings, which well, it's not going to be on the quiz, so we're okay there. Yeah, so which of the following equilibrium constants is larger? It asks, in other words, which of the forward reactions is going to be favored more? Yeah, and so maybe let's...
I think it's going to be the second one.
Okay. Let's see. This is what... Oh, what am I drawing? Okay. So here's this hydrogen, and then there's 3 phenols. Right? And then, well, there's a strong base. We're not so worried about what the strong base is. And then here we're forming this anion. Okay, and then down here we have a hydrogen here, right? And then we form this ring with the minus charge. So, well, it's already drawn out for us here. So what, Paul, why'd you say the bottom one?
Because it's going from anti-aromatic to aromatic.
Oh, is it? So where's the structure anti-aromatic?
Because it's 20. I might be wrong. I just did it in my head. I didn't actually.
Yeah, there's 6, and then there's 6, and there's 6, right? But this is sp3.
Oh, so it's non-aromatic. Okay.
Yeah, so this thing is actually non-aromatic, right? And then what do we get here?
Wait, the left we said was non-aromatic, you said? Or-
Yeah.
Okay. And it's non-aromatic, sorry, because of the sp3.
Mhm.
Okay.
Yeah. So for this problem, just consider the inner ring. Don't worry about the phenyl group so much. They're just there for consistency with the top part, because the top one also has 3 phenyl rings, so you want both to have 3 phenyl rings. But otherwise, I guess just focus on the triangle.
So for the bottom one, we're going from sp3 to sp2, right? That hybridization.
And if we're just, sorry, I cut you off. Go ahead.
No, I was just gonna say, I thought that would be the same change for the first reaction as well in terms of hybridization.
Yeah, it is.
If we're not considering the phenyl groups as part of the conjugated system, then it goes to anti-aromatic. Then we don't like that reaction.
Yeah. Yeah, exactly. Right. So this is really low. Okay. Well, and that means that K1 will be bigger. Yeah. That's pretty much it. Just the fact that you make something that's anti-aromatic, and that's going to be bad. Yeah. The reason that you have the phenyl groups up on this molecule is because you can't make this anion without it. Like this is fairly stable as is just by resonance. So that's always good.
I guess what just confuses me is like, how are we, like, I understand creating an anti-aromatic, like that's going to be a slow reaction, but like, how are we comparing that to something that doesn't have, like with the top reaction, like there's no aromaticity to begin with. So like, I don't know, it seems like we're like comparing like apples to oranges almost, but.
Yeah. I guess the thing to keep in mind with aromatic or anti-aromatic is that aromatic is more stable than you would expect. Anti-aromatic is less stable than you would expect. So for example, like, let's see, what would be a good example? I mean, like if you have just a linear molecule and you put a plus charge on here, a minus charge on here, let's make it a minus, and then you have a molecule with the same number of carbons and the same number of double bonds, but it's cyclic. This is more stable, despite the fact that it has pretty much everything else the same. And it's more stable because it's aromatic. And if it's anti-aromatic, it'll be less stable than you would expect. I think actually, I didn't watch the full lecture, but I think Dr. Tong kind of like was making this point, at least it seemed like it was in his slides, where if you had like, let's say now as a, I think it was drawn like this way in the slides. If you have this molecule, which is linear, then this is like, then this is more stable than this molecule, which is cyclic. And the reason is because this one's anti-aromatic. So it's like, because it's anti-aromatic, it's less stable than you would expect.
Got it. So it kind of seems like whenever you're comparing linear to something that's cyclic, or the cyclic, determine if it's anti-aromatic, and that would be less stable than something that is linear with the same kind of like formula.
Yeah.
Okay.
So like up in this example, we made an anion that gave us a minus charge. We also made an anion that gave us a minus charge up here. So those two things are the same, but down here it's anti-aromatic, and up here it's neither. In some sense, you can call it linear because it's just one point, but the fact that top minus charge is like just normal, and the bottom one is anti-aromatic is what causes it. Paul, you were about to say something.
I was just gonna say thank you, and I'm gonna head out. So
Okay, yeah.
thanks, and I'll see you guys.
This is the last problem too. So okay.
Yeah.
I guess see you guys next week.
Thank you so much.
Yep.
Yeah.
Bye now.
Bye guys.